So tonight, class 14, adversarial machine learning. I did finally get the student notebook working. So that's up on GitHub. We'll talk about that a little bit during the class, and we can kind of go from there. All right. So I'm just going to skip a bunch of slides here and get right into it. So we've done the ground rules and everything else. And I think I'm just going to jump right ahead to the content, right? All right. So tonight we're talking about adversarial machine learning. We talked about this a little bit before. And what is adversarial machine learning, right? We're manipulating inputs to fool models. Um, it's like an optical illusion. We talked about the stickers on a stop sign, hyperface, and that kind of fun stuff. And basically what someone's trying to do is they're either trying to get past your model or they're trying to figure out what your model is. So we'll talk through all those different things. So it's critical because attackers can exploit your ML models, right? Which is the basis for AI. Artificial intelligence is not intelligent. It's people using ML techniques to get a signal that lets you take action. And what we're trying to do in adversarial machine learning is we're trying to either not give you a signal or we're trying to give you false signal. And we can do this by changing inputs, and we can bypass defenses. And it's that arms race concept that we talked about, right? It's like LEET with two threes and a plus sign instead of LEET. FR33 instead of free, right? Everybody gets a spam email every once in a while that has something like this in the content, and they're bypassing your model, right? Malware detection, you can modify the code slightly to make it look benign because of some of the techniques we talked about being close to the decision boundary. And this is what we're going to discuss a little bit more tonight. So think about it, right? Daily, you use systems that use ML, probably spam being the most prevalent. And you've seen every day probably an example of that being bypassed. All right. So what's the impact, right? So there's three kinds of attacks that we have. We have an evasion attack, which is what we're going to talk about. That's the main focus, right? Where we modify the input at test time. This is hard enough to demonstrate. Some of these other ones are even more. I mean, some of it's even into theoretical. Poisoning, where the attacker is going to corrupt the training data. So you're training on bad model data. And they're able to manipulate the results. Like if you uploaded a bunch of stuff to VirusTotal that was marked as benign and it was really malicious, that might be an example. They do a pretty good job of filtering it out, but there might be other avenues. And then model extraction. This is pretty cool. I like nerding out about this stuff. It's where the attacker steals the model itself, right? You could query a Cloud ML API to reverse engineer the model or steal IP theft. So an example, in 2016, there was a study by researchers at Cornell where they showed they could extract the ML models in Azure Machine Learning as a Service. So if you used Azure Machine Learning as a service, people could figure out what your models were and what the weaknesses are. So they did this by being able to send queries, and they were able to reconstruct the decision tree. Remember, we talked about decision trees. It's that, is this spam example from, I think, maybe class 2 or 3, and logistic regression models, and they did this pretty well, right? So they were able to replicate the model locally because if you are able to get the output, you can manipulate the hyperparameters and figure out what the inputs are, and you could steal that, right? But the big thing is that there's potential weaknesses. There's another one. This is kind of cool. This is super nerdy, but people figured out how to use electronic test equipment to pull the model out of a TPU hardware that Google produced, like Google Edge TPU. And it was with a company called Keysight, which is they do precision side channel measurement tools. And this is like a complete another realm where this would be like, could somebody figure out how your hardware security model works by using these same techniques? Yeah, you bet you could. So this is a real issue now. It's not something that we can do with anything in this class, but it's just something you should know about, right? So this is kind of what they did is they, literally had oscilloscopes and probes and all this other stuff. And what they would do is that they would change the hyperparameters of the model and they would see what the corresponding electromagnetic output was so they could see what they were affecting in the model. So this is the extent that, the arms race has gotten to. So even if you say, oh, it's in hardware, it's secure, it's not necessarily true. All right. So let's talk a little bit about the lab. Tonight, if you open the notebook, there's some of this stuff that it takes a while to run, and I apologize I didn't get this model out earlier. But basically, what we're doing in this model is we're using the a standard data set that comes. It's called CIFAR 10. It's a 10 class image classification, and this uses what's called a convolutional neural network, or CNN. And this is what does this grid processing. And I'm going to jump ahead here for a second. So it's like this. It's a 3D model, and it takes like the input of a cat and it does this three-dimensional analysis of all of the pixels, and then it comes up with what those gradient values are, and it can change each individual one so that it can manipulate the image. All right, so if you look at the example in the lab, right, we've got our true predictions, right, which are based on the CIFAR images. And what we're doing is we're adding perturbations into them. And you can notice these because they're exaggerated. But basically what I'm able to do is I'm able to change parts of this image, and I'm able to get a different prediction out of my model. All right. So we already talked about this. All right. So here's the thing about adversarial examples is usually the perturbation is slight, because if you think about what that decision boundary is, what's the plus minus on that, where I say, this is okay, I'm going to accept it, right? It usually goes down into the negative a bit. What I'm trying to do is I'm trying to change the minimum amount associated with that particular item so that it will flip the decision over from being anomalous or potentially malicious into being something that is accepted. So I'm trying to sneak things through that might be manipulated, but I still want to get a result. So, if you could figure out a way to do this with your license plate or something like that, right? That would be an avenue you could use to defeat computer vision, things like that. So uh, it's really fascinating, but by the same token, it is less than intuitive, but hopefully some of these examples will make it more straightforward. And then a couple of things we're going to look at is we're going to look at the original images next to adversarial versions. They've been magnified, so you'll be able to see the difference, but maybe to the computer, it looks almost the same, but the model sees it as something completely different. So, we look at robustness, which is how often attacks succeed. And then we need to measure that. And then we can also train our model using adversarial training. And it kind of vaccinates it. It exposes models to the attacks during training so it can learn to recognize and resist attacks. So, and then we'll compare, using scientific method to defended versus undefended models, and we can quantify the improvement. All right. So how does it work? Basically, we start with a correctly classified image, right? The model identifies it as a ship, a truck. And then we calculate the gradients. How much would we changing each pixel affect the prediction? We do this a lot of times by making a change and submitting it over and over and over again and looking at the result. And then we basically use that method where we saw the cat with the cube, right? Is we pick a perturbation that moves things in the worst direction for the model. And then the result would be maybe the image still looks like a cat to us, but the model would think it's a dog. And again, these are exaggerated. They're by 10 times, so you can see the obvious difference. But if it was just 1x, maybe you couldn't see the difference between that original image, even though it's pixelated, and the adversarial image. So the defense really is you generate the adversarial example during training. You'll train on a mix of clean and adversarial examples. And then the model learns that suspicious patterns are actually still cats, and a more robust model will be harder to fool. So for attack, it's like learning someone's weakness to exploit them, right? We keep picking away. It's like a probing attack. I want to see what happens when I do a particular thing, and maybe I need to adjust the strength or direction of my attack to achieve the result that I desire. And then, as far as defense, we're looking at the strategies because attackers have patterns, computing has patterns, and then we try and determine what is the best strategy to defend. So, adversarial training is super important to making this work. But then the question you have to ask is, what trade-offs do you make by making the models more robust? And we'll look at those a little bit as we go along from this. All right. Okay, so we talked about this a little bit, so we can kind of breeze through this, but basically we're taking a correctly classified image, calculate the gradient of loss with respect to input pixels. That's going back to that model where we have that cube, the CNN. And then we add small perturbations, and we look at the direction that maximizes the loss. And then if you aren't exaggerating it for the standpoint of an example, you will find that the images will look pretty close, but they get misclassified. And then again, when we defend, we train the model on the original and adversarial examples. And, again, we can use supervised techniques for this. And then adversarial training makes the model more robust. So basically you're making the model work harder, and it improves its ability to make decisions. And that's how you get that better accuracy. Okay, so if you look at our example here, we've seen some of these out, and you can follow along in the student notebook. We have a cell for each one of these, sorry, right? So we're talking about how FGSM attacks work. We'll talk about that. We have a checkpoint, and then we can see, what is the model confidence? And you can see here that when you have these original images and then the adversarial results, they get misclassified. And then what we're looking at here is what's the confidence of the model. Now, this is important. We want to talk about this, right? Is that when you look at this, you can see that the original model, because of the confidence, right? Even if it's an actual image of a horse, it's only, it's less than 60% confident. But because our adversarial model is pushing it in a different direction, and we're not humans looking at this is a model looking at it, so it knows mathematically how to do this, it's able to push it in a different direction, right? So it can say, instead of a truck, it's a horse. And it's the same thing with, cat. You can make cat think it's a dog because you change the adversarial, the model. And, you've got a couple examples of the same thing. All right. So let's talk about FGSM, which is fast gradient sign method, right? And this is how we do that analysis. So this is the actual gradient analysis. So if you look at the visual analysis, like this grid breakdown, and you look at it from left to right, so the top is the original image, right? And it's a clean CIFAR image. It's correctly classified. And then this gradient magnitude, this is what the CNN looks at, and it sees what's most important. And you can see it still kind of maybe looks like a bird a little bit. And same thing. You've got a horse, and then you've got the gradient magnitude associated with it. And now what we're doing is we're adding this sign gradient in the attack direction. And you can see that even though a human could look at this and say, yeah, I still think that's a bird, we've convinced the model that it's a frog somehow. Maybe it's the eyes on top. I'm not sure exactly, but we've basically manipulated this image and we're making it think it's a frog, right? So if our model says we only allow bird pictures to be uploaded to our site, and somebody could subvert it somehow, I'm kind of reaching here for an example, this would be a way. And we're doing the same thing with horse. Now, horse to deer, that's a close enough stretch, but it still kind of shows how we're generating these adversarial examples. And if you look at FGSM, basically the gradient magnitude, which is these kind of cool looking things that are next to the original magnitude, they show how sensitive the model is to changes in each pixel, right? So it's basically a heat map. And if you look at the attack direction, you can see red is quote unquote hotter, right? And it sort of corresponds to the heat map, the gradient attack sensitivity. And that's basically what wins it over is. But so I make those changes, and even though to us as humans it's like, oh, that's pretty obvious, it's the same thing, to the model we're able to fool it, and it's misclassifies. So it's basically, the key insight is this: the attack patterns are different for each image, so they're customized. There's not one size fits all. The bright areas in the gradient magnitude show the weak spots in the model. This is like if you've ever done TensorFlow image classification and training, you look for neurons that spark, kind of same thing. And then the attack direction looks like random noise, but it's precisely calculated using the CNN. So that's kind of the high level on that. Deep subject, there's a lot you can delve into here. All right. And then from there, we talked about this a little bit. We kind of touched on it. This is the model confidence, the original versus adversarial. So if you look at this first example and the first chart, the truck example, right? The model was 55% confident it was a truck, and now it's 100% confident it's a frog, right? So so that's that's an example. And actually it would be a horse. I don't know where this is from. But anyways, so the cat example is that it completely shifted, right? We went from cat to dog, and the same thing in both examples. So this shows how the attack completely fools the model. And certain classes, like with animals, cat to dog is a common target, so maybe there's a little bit more intuition about how to do that. Then we talk about the attack success rate versus epsilon. right? Epsilon is how much change we're introducing. We talked about this before. So the attack strength is on X, right? And the success is on the Y. And the success rate plateaus around 67%, right? And that just kind of shows you, so you wouldn't need to have an attack strength stronger than 0.05 to generate basically the same result. So less is better. It's less likely to be noticed because you're implementing less changes. So as far as implications, right, in security, this overconfidence and wrong predictions is dangerous. And you could have a high confidence in a malware detector that something is benign, but maybe they're able through techniques to slip stuff through. That's why you got to continually retrain your models and make sure that you use ensemble techniques like supervised and unsupervised to validate your results. And we talk about robustness, where we need to make sure that we're testing for this in systems. And then you need to think, some things might be more robust than others. I don't know, like pizza and a dartboard, I think are probably pretty close, but a brick and a ball, you'd probably be further apart. And again, the epsilon value is how much change, and you want to do the least amount of change. This is sort of like the elbow method that we used previously for K, except it's a different direction, right? We're trying to make change, and we want to make the least amount of change. So we test different values for the attack strength, and we want to use the lowest one. Okay, so how do you defend against adversarial attacks? Um, basically you have to look at the classes and figure out what's vulnerable and what's not. So you need to train on a combination of clean and adversarial examples. Your CNN learns to ignore superficial patterns and focus on the characteristics, right? So this is I guess analogous to feature reduction, right? We don't want to look at everything. We want to look at the most important things. Um, if you've ever tried to focus uh, and ignore distractions, sometimes that's a learned behavior, maybe noise canceling headphones, but you employ methods to make sure that you can focus on the important things. And then your CNN learns what's truly important about each class. And that's kind of what we're looking at here is, what's the specific vulnerability to FGSM, right? Where we have this epsilon value, and you can see that it's pretty high. And then you can see the most and least vulnerable classes. You see there's not a big difference. And this is the margin, right, that our adversaries typically exploit, is this little bit of gray area. So even we're going to talk about how we train models so that they're more resilient and less susceptible to adversarial attacks. And we're talking about trade-offs, and we'll get into this in a little bit. So again, no defense is perfect. It's an arms race. We're just trying to be a little bit better than we were before. New attacks are constantly developed to bypass defenses. We're going to see some significant examples of that here in a minute. And there's trade-offs, right? Robustness versus accuracy on clean data. And this is sort of back to what we've talked about previously with respect to confusion matrix and things like that, is where do you want to make a mistake, right? Do you want to have a lot of false positives and make sure that we catch all the bad examples? Are we willing to accept some kind of trade-off? So you need to think about that, right? Because there's costs and benefits to each one. Okay, so when we trained these models, we looked at kind of their accuracy and how good did we do when with respect to validation, right? So we have standard training and then we have a robust model. So basically what we're saying is this is it better for me to train a robust model that is less susceptible to adversarial techniques if maybe it doesn't catch as much on the clean model side? So this is back, if you think about the confusion matrices that we've looked at previously, that is it better to reduce the number of false positives with there might be some false negatives get through, right? That's a decision you have to make. But basically, this is where we're at with adversarial, because you'll see here in a minute that the adversarial examples, when there's adversarial images sent to an untrained model, its robustness is very weak, right? Its accuracy trends towards zero. And if you have a robust model, it is much better performance, but you still have to accept the fact that there might be some bad stuff that gets through. So with respect to what we've done here, I'm not going to get into all the speeds of feeds, but I want to kind of make sure there's some key points that we dredge out here, right? First is that there's a computational cost. When you guys go through and run the student notebook and do the lab notebook, you're going to find that there are some training methods that take a fair bit of time depending on your machine, right? So it takes longer and it's obviously going to use more resources. Think about doing this at scale, right? Um, it takes longer to get model convergence, right? You got to learn more about the decision boundaries. And then there's a trade-off, right? There's lower clean accuracy, but better security. So that is a key takeaway from this, right? Is that it's more robust, I catch more stuff, and I can deal with the adversarial, but I might miss something from perfectly clean data. All right. Okay, so what are some of the challenges against defending against adversarial attacks, right? So this is the broader implications of the arms race, right? So we've talked about this. Attackers develop new attacks, defenders create new defenders, attackers adapt. It's spy versus spy. It's antivirus and malware have evolved doing the same thing. It's like, oh, we have a new thing, and then it's immediately irrelevant. Um, there's no permanent solution. You always have to be evaluating your models and retraining them. So this is where you bring value as the AI wrangler, because if your leadership thinks they can just buy software and put it in and use it out of the box and there's nobody looking at these things, right? They're probably not going to get the most value from it, right? Because this is similar to what I've talked ad nauseum about detections in Sims and things like that, right? That's somebody else's idea of what is wrong or or what you should pay attention to, and it may not necessarily have any relevance to your environment. I know there's people I've talked to, and I've said this before, who spend part of their day looking at false positives and classifying, right? It can get expensive. There's a lot of analyst hours that are spent doing this. Um, but uh, it's I would rather spend work training a model that can reduce the amount of the false positives than just going through and writing up exception reports or something like that. So challenges are, it's expensive to train, right? Both there's some human effort and computational cost. Um, the analogy I used about having a bag over your head and being in a boxing ring, how do you defend it against attacks you haven't seen, right? This is, we're looking for anomalies again. And then, if I figure out how to attack one model, I can also figure out how to attack another. Stop me if you've heard this before. What are some other defense mechanisms? Right, input sanitization, right, pre-process the inputs, remove adversarial perturbations. It's a spam filter for adversarial records. Anomaly detection, right? Detect when an input looks suspicious, as opposed to it being automatically classified. Flag it for a human, right? This is I think it was the DDoS example we used that classified the attacks, and it said which ones are high priorities, right? You can do this with the adversarial machine learning too, and there's tools at your disposal. This is for you to look into, like the adversarial robustness toolbox, and there's more. And I would suggest you look at these in your own time if you're interested, because there's a lot that goes into this that we're not ever going to be able to cover in the course of one lab. Okay. All right. So let's talk a little bit about the model performance. So, and then we'll get into the notebook a little bit more, right? So this is really the tail of the tape for the demonstration, right? Here, this is what we've been talking about this whole time, is the difference between the model performance between clean images and adversarial images. Now you can see that with clean image, right, we have good performance from both the adversarial and the robust model, but the robust model isn't as good as a standard model. But when we start passing adversarial images to it with respect to classification, and this is the actual results from the notebook, this isn't just something I made up, you can see the difference in the model, right? So, 98.9% of adversarial images got by the standard model. And you can see there's a big improvement, like a 50% improvement by using the robust model. So are you willing, this is a decision to make, right? Are you willing to take that 2% hit on clean images to get this against adversarial? I think it's worth it. So, this is kind of where we're going with this. So, again, the standard model is like 1.1% defenseless, right? Might as well not be there. And what's the ROI, right? It's the 3.2 accuracy cost for almost 50% robustness gain. That's a pretty good trade-off. And, would you rather detect 50% of the attacks or 1% of the attacks? Right. So maybe you think about it different, right? You're going to get somebody who says, I want to detect 100% of the attacks. Well, there's a trade-off, right? We may be more susceptible to adversarial kinds of things. So it is, there's a big difference between something that's usable and something that's broken, right? If I'm able to subvert this by submitting adversarial attacks, then I've essentially your system is worth this. So again, perfect security doesn't exist. We optimize and we do acceptable trade-offs. With respect to the threat model, these results assume that we're doing FGSM attacks. If there was stronger attacks, which there are, and it's maybe on the scope of this course, we might use a different defense. And then you have to have a discussion with your leadership and based on your specific business needs to decide if this trade-off really works. So this is something I learned at Google, and it was basically this. Sometimes it's better to spend 20% of the effort to get 70% of the result than to spend 100% of your effort to get 100% of the result. Because if you're doing 20% of the effort and getting 70, you can do that 5 times for the same amount of effort and get a lot better result. And this kind of falls into that same boat, right? So malware detection, it's better to catch half of adversarial malware than 1%, right? Because we sort of see the results here. you know, if you're doing fraud prevention, you have to balance a false positive rate against adversarial robustness, right? To see what is acceptable in your environment. Again, it's probably better to catch half of the bad things than none of them because your accuracy is higher. And the costs are high if they fit, right? If malware gets in, if ransomware gets in. And these are all discussions that you need to have. Okay. All right. So that's a lot of talking. So let's talk a little bit about the notebook. So I created, you can follow along with this. I ran all these previously because some of them take some time to run. So you can download this notebook and run it on your own machine. But basically what I did is, based on the feedback that you want to have more hands-on, here is an example, and I wanted to leave some time to go through this and then answer some questions at the end, right? So we have our basic, standard preamble where we do the setup, we do our imports, um, we have our configuration. These are the hyperparameter tuning, right? You could change these if you like. If you the epochs are basically how many rounds are you going to see when you change epsilon, what the impact is, and you'll see this as we get down in here further, right? So the first thing is there's a markdown cell, right? So what is the threat? We talked about these, that perturbations are small, and those visual examples, those are 10x, right? So you could see them well. You may not even have to have a 1x change, so it would be something maybe that would be imperceptible to humans. And why do adversarial attacks matter? If somebody figures your model out or steals your model, they're going to be able to submit things that might bypass your security system. And again, this is the question you ask the person who sells you the super cool AI enabled security gizmo, right? Is, how do you train for adversarial attacks, right? How do you update your model? Those types of things. Um, facial recognition, we've seen this. I talked about hyperface, and there's lots of ways that you can evade recognition. There's been lots of things that have been done over time with, masks and models and things like that. And people are trying all your models all the time. And any ML system is potentially vulnerable. We've talked about some of these techniques before, because you train your model, and what if I'm doing something like packing, where I'm putting code in a feature that you're not monitoring for your model, so I'm able to chunk some code in there and access it later, right? I figured out a way to get past your model. So maybe you need to retrain your model and say, oh, if we have this anomalous file size of this outlier in a feature that isn't part of our model, maybe we want to flag it anyways, right? So that's your hypothesis, is what is it about ML models that makes them vulnerable? So you can put that in there. Okay. So then we're going to define a demo class. And this is basically the model where we're going to pull the data in, and the CIFAR 10 data is what we're using. And we're pulling it in, training it, and loading it. This is beautiful because this is all done for us. It's part of scikit and maybe TensorFlow, but you're basically doing the import. This is part of your Python kernel, and you can access it using this code that we're running. So we get that, and then this is the result. These are the images from the CIFAR data set. We're just showing an example of them. I think there's 50,000 or 60,000. I can't remember, but it's a pretty good sized data set. So the second thing is that we're gonna create a vulnerable model, right? So this is a normal CNN that hasn't had robust training. And this could be any model that you used in ML, right? And if you look at the images above, these are the 10 classes our model will learn to recognize, right? So it's going to look for frogs and birds and horses and stuff like that. And there's many samples of these in the particular data set, in the SciFi data set, and they've been classified. Okay, so now the next thing is we're going to train the model. This is the stuff that is going to take time. So basically what we're doing is we're training through many different cycles. And what we're coming up with is our training accuracy and validation accuracy for this particular model. So if it takes the images that are in the SciFi data set and evaluates them, this is the accuracy and stuff that it will produce. So and this is pretty standard. So if you run this, you want to know what the final accuracy percent is, the final test accuracy, and how long did it take to train, right? And it's gonna the vulnerable model doesn't take as long as the adversarial model. The adversarial model takes a while. On my Mac, it takes a while. I'm sure on something that probably doesn't have as much GPU as that, it would take even longer. Okay, so now we're going to look at the FGSM attack, right? So FGSM, again, fast gradient sine method. And, we got a bunch of code. So this is kind of the result, right? So what we're doing is we're taking our truck, right, which in our vulnerable model, it says that my confidence that this is a truck is about 76%. And I add some perturbations in, which are quite visible here. I think you could also say that's maybe a stormtrooper helmet or something else, but I don't think that was in the SciFi data set. But now it's basically saying it's an automobile by making those perturbation changes. So it's almost 100% sure that it is, right? So let's look at a few more examples, right? So we're using a kind of a lowish epsilon number, and remember epsilon is the amount of change that we're using for FGSM, and these are the results that we have, right? So if you look at this, that looks like a bird if you kind of stare at it and squint, and by adding the perturbations in, and again, no human is going to look at this, only the model, it's changed that prediction to a frog. Same thing with our prediction here is it says it's an automobile. We add some perturbations in it, and now it looks like a dog, right? Does this look like the actual dog kind of catty corner to it here? Yeah, maybe, but I'm not an algorithm. I'm a human, so I have a better processing wetware that takes care of that. But it again, it changes the prediction. So then same thing. My original is that says it's a dog, it predicts a frog, so it was wrong on that. And it's the same thing, right? Ship, airplane, truck to frog. And I guess I could see how you can get from truck to frog. So the attack rate is 80%, and that's pretty startling, right? To go from a model that is what it was at 76% accurate to have it be now like way less accurate. And we fooled them all 4 out of 5 times. So you can fill this out yourself if you run it. So the question is, right, as a human, can you tell the difference? Answer is usually yes, but your brain and your eyes are much more sophisticated than a computer algorithm. It's using numbers. You have the context. Again, that's why humans are never going to go away, to tell whether this is true or not. Now, could you do this a million times? Probably not, but you can look at this and evaluate kind of where the model is going. All right, so now we're going to talk about,
Question
yes.
on that. Kind of a two-part question is like, Why are the images so grainy? Is this like harder to do on like a higher resolution image? And kind of related to that is like, is that why CAPTCHA images are purposely pixelated in order to fool potential computer generated like solving machine algorithms for it? Is it
Yep.
like that?
Yes. Yes to the captcha question. And the reason that these are pixelated like this is that's the way that they come from the sci-fi data set. And the processing that you would need for a more fine-grained image would be horrendous. And it would be really hard to do this demonstration. So I think the sci-fi is intentionally pixelated just to make it easier for doing machine learning experiments and training and things like that. I have seen examples where they used uh, more detailed images, and it takes a long time to run a model. This model takes a long time to run as it is with the sci-fi images, but I think your point is yes, it would be much more complex because the CNN would take longer to render. You know, if you think about that 3D cube, and each if you have more pixels, you would have a bigger cube, and it would just take more processing power. Did that answer your question?
It did. Thank you.
All right, cool. Sorry. All right. So now let's talk about the attack mechanics. We looked at this a little bit in the slides, but here it is in your notebook, right? So what we're doing is we're trying to figure out, again, epsilon is 0.1, smallish, but not really super small. If you had a more detailed image, you might be able to get away with a smaller epsilon, maybe, but this is kind of what happens. So if you look at this, you can see because this perturbation is so amplified. If you could imagine the perturbation overlaid on the original, that's kind of what's happening. If you sort of squint and look, you see the original and the perturbation. It's like those two are overlaid and you get the result at the bottom. Now, could I believe that's an airplane? Yeah, I could believe that's an airplane. But you see kind of the progression here, which is sort of cool, right? So I have this original, my Roblox ship and my Roblox trucks, and then I add this perturbation to them and it thinks it's something else, right? So this is pretty amazing, right? Because this doesn't look anything like a horse, an airplane, or a frog, maybe to a human, if I squint and kind of look at it. But if you think about the model and it's evaluating the gradients and doing the CNN is tearing apart kind of this 3D example, this is sort of what is going on. And again, it's like an overlay. If you take the original and you overlay the perturbation, again, this is 10 times amplified, so you probably wouldn't see this if it was just one time. I guess maybe I should have done a visualization for that. But you can see the result, right? So you can see that pattern, like I've got this green square up in this corner of the original truck in the on the right hand. And then if I look down in the result where it says it's a frog, I can still see that same kind of green square, but it's mashed up with the gray. That's what's going on with respect to this. Okay, so that's part four, right? So we're asking some simple questions, and there's other questions in the hands-on student thing, right? What do you observe about the perturbation, right? Do you see that overlay between the original mashed up with the perturbation and the result, right? And could you see how an image classifier could make a mistake, right? This is a standard, this is no funny business, right? These are standard images. This is using TensorFlows as far as a model. So this is the same kind of stuff that you would use in production. It's not like one of my hokey uh, synthetic data deals. And that's why this is so cool, because we're taking a step back from synthetic data. And although the perturbation is somewhat amplified, this is still real sci-fi data, right? So these are real images. Okay. And then, you know, again, computers are not as good at looking at things. They look at them differently. This is all about math. This is not about does it look like a thing or does it look like another thing? And that's how we're able to fool it by doing these perturbations. So here's your checkpoint part 4. Okay, so now we're going to talk about confidence, right? This is how confident are we of the original versus the adversarial? So here's what the original truth is, that we have that it's a bird, right? And then we've got adversarial that says it's a cat. Depending on what your confidence is, right, you may be able to misclassify it as a cat. Same thing with horse and deer, right? We saw that example up there previously where it said, no, that's not a horse, it's a deer. It's close enough, right? It's above that 60%. So it doesn't recognize it as a horse anymore because of the perturbations, and it thinks, well, it's close enough for a deer. And same thing here, right? It says the truth is the frog. If we have the adversarial model, it says it's a deer. It could be a horse, depends, right? Horse and deer look awful alike, but it's not going to be a ship or a truck. So this is sort of an example of what the confidence change is. So you ask yourself, right, is it more or less confident in wrong predictions, right? Maybe it's more. That's back to what the original confidence in the model is. We haven't trained any adversarial capabilities into it, so it's just basing this on its like base decision. So ask yourself this, right? Does it become more or less confident? And then there's some other questions about class targets and things like that, but take a close look at that and see if you can answer those questions. Okay, so now these last 2 cells, I got locked out of Claude. I had to wait because I used up my 5-hour amount of tokens and stuff like that. I've been trying to thrash on this for 2 days to get this to give me the same result that I got in the demo. And like literally while I'm doing one-on-ones in the 20 minutes between, I finally got it to go. And this was a classic AI thrash where I had to switch the chats a couple of times, but I finally got it figured. Okay, so now we're going to do adversarial training. I will warn you, this is going to take some time. I think it took 20 plus minutes probably for me to do 5 epochs of adversarial training. So basically what I'm doing is I'm training a robust model by feeding it uh, adversarial examples, and I'm trying to get it to recognize those attack patterns that we looked at, like those perturbations, and improve my accuracy. And we'll show you why in a minute, right? If you remember what we looked at before, the performance comparison with the adversarial images and the robust model, right? If I introduced those perturbations, I would get like almost 99% failure rate of my original model. So this is something that is important to do, is this adversarial training. And this can apply to everything that we're doing here. We haven't really talked about including it as part of your capstone project, but if you're doing this for real, it may not be a consideration when you're doing your initial experiment. But if you're going to deploy a model, you should ask about adversarial training. So, hey, Mr. Systems Engineer, for that whiz bang AI box that my CISO bought that solves all our problems, how do you guys handle adversarial training? Right? Ask them that question. See what kind of looks you get. Right? This is part of you being the AI wrangler, right? Is you know how to ask these questions. So let's make the SE and the sales guy from the box company a little uncomfortable, and we'll make them work for their commission a little bit harder. Um, so what we're looking at here is, again, right, our robust model clean accuracy, so non-adversarial images, is a little bit lower. I think up there it was like 76%, now it's 64%, so it's less, but the adversarial accuracy is 50% as opposed to like 1%. So this is where we stop those attacks by training this adversarial model. So then we look kind of at this last little bit of code. This is the presentation part that I banged my head against for a long time because it wouldn't show me the correct adversarial results. But this is really what we're getting down to here is let me see. I should have done this before. Right. So we got larger images. Okay, so then we do the final model comparison, right? So this, again, this is the same epsilon we've been using the whole time. You can change this at the top in the hyperparameter tuning. And what we're saying is this, is the standard model, its clean accuracy was 65%, but its accuracy against adversarial was 0. So that's not very good. But if we do a robust model, actually its clean accuracy is a little bit better, and its adversarial accuracy is way better, right? So I think these results are a little bit off, but because it says the clean accuracy lost is minus 1.5%, so it might have transposed those numbers. I didn't notice that. But the TLDR, right, is that it's a huge improvement in adversarial attack resistance. So you need to ask yourself, is the trade-off worth it, right? And you have probably heard this. I've heard this a bunch in my career. Oh no, we have to be 100%. Get real, right? That's anybody that says their model is 100% accuracy, they should just leave, right? Because that's never going to happen. It's all about trade-offs, right? It's the same thing like we talked about with looking at confusion matrices, right? Is what's the trade-off? Am I willing to have 15,000 false positives to make sure that I get 34 uh, true positives? Or can I maybe say I want 5,000 false positives for 30 or something like that, right? You need to make that business decision. But but remember, there's a cost. There's a cost in compute. There is a cost in analyst time. There's fatigue, right? What should I be doing instead of going through and filling out the false positive report? What are you doing with that information? Why aren't you training that back into your model? Why aren't you doing supervised learning with your false positive reports? I mean, that's something that anybody could do using these techniques. And then that's the trade-off that we're looking at here, right? Is we understand that a 1.5% reduction in accuracy is worth a 59% improvement in our ability to resist adversarial attacks. Okay. So and then here's the flat out I guess the tail of the tape, right? This is the effectiveness is, would you take that percentage of accuracy improvement for a 0% accuracy against adversarial attacks? If you were able to show somebody this, they would probably say, no, thank you. Okay. So then you can look at the final observations and fill in. Okay. So that was a lot. I want to stop, take some time to do questions. Uh, any we've come a long way. We talked about stickers on road signs. Now we're talking about perturbation of sci-fi images and things like that. Anything anybody wants to kind of throw out there? We got a little bit of time today. Yeah, Jose.
I have questions not so much on today's topic, but more on the assignments.
Yep.
Question about like going through the assignments. Assignment 4 was very robust, had lots of different steps that we did. In
Yep.
comparing assignment 5 and 6 to assignment 4, like what is the primary like difference between assignment 5? Because I know we're doing a lot of the same like data import and like
What I
train
was trying,
different
that's a good
models?
question. What I was trying to do is I was trying to structure those so they followed the machine learning life cycle. And maybe that didn't come across in the assignment, so I can, maybe try and shore that up. But what I was trying to do is I was trying to take you through the machine learning life cycle. So, you pre-process, you prepare, you build the model, you test and do that kind of stuff. And that's what I was trying to get across. So
But I guess I'm trying to understand like the actual difference in assignment 5 to 4 because it seems that in assignment 4 we did, or maybe I'm getting confused, but I think we did train our model, but maybe it was, I'm trying to remember if it was supervised in 4 and then 5 is more
yeah, there
unsupervised.
was unsupervised, and then there was supervised in four, I think unsupervised in five, and then assignment six was choosing the best model or ensemble method from the two. So as you're going through, right, you want to try, if you have ground truth data, you want to try and do supervised learning. And then also if you have ground truth data, you can use that to test and see how good your unsupervised is. And then there's probably an ensemble between the two that's going to give you the best result. And that's what I'm trying to drive towards.
Okay, got it. And then basically our capstone is essentially like that same progression of 4 through 6.
Exactly.
Uh,
And you just do the final analysis on it. And that's what my intention was, is that it would build so all this, basically what I was envisioning is you would be able to do all this in one notebook, and you wouldn't have to do a bunch. You would just do versions of and add the stuff in. And that's what I was trying to get to.
okay, so 5, so assignment 5 should basically be in addition to, like if we take our assignment 4 notebook and we just add assignment 5 to it, and then so that's, we can basically
Yep.
start with assignment 4 and then continue on for the rest of like 5,
Yep.
6 capstone.
That that's totally what I was trying to get to, man. As opposed to it you having to reinvent the wheel each time, that you would just add a step to the notebook each time as you went along.
Okay, got it.
All right.
Okay,
Sorry if that wasn't clear.
it's all good.
All right. Yeah, you bet. Draj?
Yeah, I also faced a similar confusion because most of the assignments had a pre-idea about which assignment to use in order to make modifications, whereas the fifth one was more on the lines of do this. But it wasn't clear about whether we had to work on the unsupervised edition of our code, and it was bit confusing. When I read the sixth one, I got like an idea about, okay, fine. So the third and fifth works on the unsupervised, the second and the fourth works on the supervised. And then you have to combine together to form the sixth one in order to develop the model evaluation and validation.
That was my intention.
Yeah, so yeah, I think that information was missing on the assignment fifth. But Professor, yeah, go ahead.
Well, no, I agree. I looked at five and I was kind of like, this doesn't really do a good job of tying everything together. So I could have done a little bit better there.
No, but I get the gist of it because all you had to do was like apply the algorithms that were involved in the unsupervised integration for the data set.
Yep.
So I had to do everything, which uh, made it easier. But I wanted to ask about like an approach towards whenever you are trying to model something. Does it actually go by like you get a data set, you identify your target column, and once you identify the target column, do you always go by you do supervised and then unsupervised and select the best model just the way you explained throughout the course? Or how does the approach go?
That's a great question. So it depends. So if I have ground truth data and I can do supervised learning, I like that because then I can go through and I can test that against unlabeled data. So it's like if I have supervised, I will train unsupervised and then I will compare future labeled data against my unsupervised
Okay.
to validate how good my models do. So it's really a combination of two. Sometimes you may not have labels. And this is why I always caution people that when you say you're going to do some fancy machine learning stuff, say it's going to take some time because a lot of times you're not going to have labeled data
Mm-hmm.
to do supervised learning. So you're just going to have to try and go through and do unsupervised anomaly detection. But once you do unsupervised anomaly detection, you need to incorporate some kind of feedback loop. And this is why, your false positive nightmare might not end at the beginning, but eventually it's going to end because you're still going to have to go through and look at the results and try and fine tune your model based on that. Right. So if you have supervised, you can do a supervised model and then you should validate it against an unsupervised model to make sure that the labeling was correct. But if you only have unsupervised, which is a lot of times it might be your lot in life, you should go through and then once you make the predictions, you should have analysts or you should do it yourself. You should go through and validate it. And then that becomes your ground truth that you use to check and make sure how good your models are performing. Does that make sense?
Yes, yes. Okay. So a follow-up question on that would be, I'm working on like a fraud data right now, to see if I can find out whether the registration or the login was successful or not.
Okay.
So in that case, I feel like I was not able to find a target column because it's not just so there is registration allow deny and there is login allow deny. So the whole data set consists of registration as well as login, but the allow deny falls for both registration as well as login. If you understand what I'm trying to get at. So it's kind
Mhm.
of making me confused about how do I approach this because I do not have a just single target column that I can focus on in order to develop my modeling strategy, just like how we did with malware data set. So in that case, how would you explain how do I approach this data set?
I would I would break it in half. It's because so what you're trying to do is you're doing two classes, right? Or maybe more, maybe
Yes.
four classes. So it's a classification problem. And what you're trying to do is you could do like k-means and k equals 4, and you're trying to do 4 classes,
Mm-hmm.
something like that, right? Because you're allowing registration, you're denying registration, and can you log in unless you register?
No.
Right. So maybe you break it up into two problems, right? So you're looking at one model and it's just like one class SVM, I'm allowing registration and I'm not. And then I look at it another thing, maybe it's one class and I have can I log in or can't I? And maybe you could
Oh,
break it down.
okay. Okay.
So, and then because if you can't log in unless you register, then it seems like it's two separate things to me, just on the surface.
Oh, got it. Okay. Okay. Yeah, I was confused on that part, but okay, I can
If that's the only thing you're confused on, you're doing pretty good.
no, I'm just trying to understand like how can I use the methodology that I learned here in order to
Yeah.
focus on my data set and get something.
Well,
I,
why don't you try that and see what you figure out, right? Because it seems like if you can't register, you're never going to be able to log in. But
correct.
if you can register, the question is, can you log in or not? Right. So it seems to me just on the surface like it might be two different things.
Hmm. Okay.
So let me know how that works out. I'm
Sure,
interested.
sure. I'll definitely email you because I definitely need some brainstorming on that piece.
Okay. All right. We'll give that a try and let's see what happens.
Sure. Thank you, Professor.
Yeah, you bet. All right. Anything else, or are we ready to call it early this week? I'm taking silences.
Hi, Steve. I have a question. For like, like Snort and Wireshark, are they also integrating AI as well? What happens with like, like if you're
I don't know. I don't know. I would say probably somebody has tried to do that, but I really don't know for sure. I would have to go and do some research. It's been a minute since I looked at either one of those. But I would say editorially that people are probably trying to rub AI and everything.
Thank
All
you.
right. Yeah, you bet. Yep, that's the answer to all the problems of cybersecurity. We'll just rub some AI on it and it'll all be better. And we'll take the CISO out to a nice dinner and what could possibly go wrong?
Well, Professor, all credits to you. I just wanted to highlight one achievement which made my CISO impressed, actually. I was able to create a MITRE attack framework with a detection gap coverage within my environment and showed it to CISO using Streamlit, and he was pretty impressed with it.
Well, good for you. I'm glad to hear that. That really makes me happy.
Yeah, like he was like, wow, that looks fancy. I'm like, yeah, it's all open source without spending money.
Yeah, that makes it even fancier, right?
Yeah. So
So
thank you for showing that. It was really awesome, actually, to be honest.
oh, good. That really I really appreciate that, and I'm glad that people are getting some results out of doing this. It's this is your superpower. I mean, it's my superpower. I just got offered a job going back to Microsoft as a principal SOC architect, so I guess I'm going to unretire and go back to work. But
Congratulations.
thanks. So but I mean, I am seeing the same effect that hopefully y'all are going to see, right? Is by being able to do this kind of thing, right, and bring stuff to the table, you're going to impress people. And we're the wranglers, we're the people whose jobs aren't going away, and we're the ones that can use the tools and techniques that we have now at our disposal to get 10 times the results, right? So let's keep that going. All right, that's all I got. And thank you all for being here. We got 2 more classes. Be wrapping up next week. And I am very encouraged to hear that you guys are starting to see some results and get some traction with some of this stuff. And to keep on chopping. It's good stuff. All right. Thanks, everybody.
Well, can I ask, please?
Yeah.
Has the capstone been assigned?
Yeah, it's out. The assignment was in the chat on Discord. Paulina, I think, has that in Google Classroom. And if you need it, I can send it to you.
Okay, so we have it in Google Classroom as well now.
I'm gonna
It
put
should be posted. Oh, I'm so sorry, Steve.
Yeah, go ahead. You're the person.
It should. Since we're finishing class a few minutes early today, it hasn't been posted, but it should go out in like 10-15 minutes.
Okay. Thanks so much. Yes.
Okay. All right. Thanks, everybody. Have a great weekend, and I will see you Tuesday.